Now, we've seen how Newton's laws have to be modified to be consistent with the principle of special relativity. Let's take a look at Maxwell's equations. And since Maxwell's equations actually told us that there is a speed c, which is a fundamental constant of nature, we might expect that Maxwell's equations are actually automatically consistent with the special relativity transformations. So let's see how we can show that. Okay, so let's write down Maxwell's equations. So Maxwell's equations, assuming the presence of a source, can be written in this form. Rho, I'm actually going to use Gaussian units here. So in Gaussian units, I can write this as 4 pi times rho. Del cross E is minus partial B, partial T. Del dot B is 0, and del cross B is plus partial E partial T, and the constant C appears over here, and this is plus 4 pi by C times J bar. So rho is the charge density, and J bar is the current density. And now if you look at these equations, it's not at all obvious why or how this is consistent with special relativity, apart from the fact that a constant c appears in both these equations, in these equations. Okay, so these are coupled differential equations, and we're trying to solve, assuming we know the sources, we would be trying to solve for the components of the electric and magnetic fields everywhere in space. Okay, so at each point in space, we are trying to solve for Ex, Ey, Ez, and Bx, By, and Bz. So let's count how many equations we have. We have, this is one equation, it's a scalar equation, a 3-scalar equation. This is a vector equation in 3 dimensions, so this is 3 equations. This equation tells us about the absence of magnetic monopoles is 1 equation. And this Faraday's law is another 3 equations. Okay, so the first equation, of course, is Coulomb's law. Then the second one is Lenz's law, and the third is that the statement that there are no magnetic monopoles, and the fourth is Faraday's law. And in total, if we count how many equations we have 8 equations. Now, what you can do is you can define what is called a field strength tensor. Okay, and if we define this field strength tensor, this is a rank 2 contravariant tensor. And if you'll recall, I told you that sometimes we just have to guess what transforms like a tensor. Okay, so if you write down a rank 2 tensor of this form, where I fill in the components of this tensor with the electric and magnetic fields, so I filled in all the entries of this matrix. So what that means is, if I take F00, this is 0. If I take F01, that would correspond to this entry, which would be minus Ex by C, and so on. Okay, and the other thing that you'll see about this tensor is it's an anti-symmetric tensor. That is, if I take f nu mu, that is if I change the indices. So for example, if I calculate f10, this would be the same as minus f01. So f nu mu would be minus f mu nu. Okay, in general for the nth and muth components. So this is what we mean by an antisymmetric tensor. Okay, and by writing the electric and magnetic fields in this tensor notation, we are assigning properties to how the electric and magnetic fields transform under Lorentz transformations. That is, we're assuming that the electromagnetic field F mu nu, or the field strength tensor, transforms like a tensor, which means that if I know the field strength tensor in one reference frame S, and I want to know what the field strength tensor is in a different reference frame S prime, then what I would do is I would calculate, assuming I know the Lorentz transformation matrix, I would calculate something like this: lambda mu rho, lambda nu sigma, F rho sigma. Okay, or in matrix notation, the matrix F prime would be lambda transpose F, would be lambda F lambda transpose in matrix notation. Okay, so if I know the field strength tensor, that is, I know the components of the electric and magnetic fields, and I know the matrices lambda, which relate to frame S and S prime, I can get the field strength tensor in the new reference frame. Okay, so this allows me to get the new field strength tensor in frame S prime. And of course, once we have the contravariant field strength tensor, we can also define the covariant field strength tensor, F mu nu, using the matrix G, the metric, to lower and raise indices. So we can define something like this, okay, which gives us the covariant field strength tensor. Which in matrix notation, I can write down the components of this as like so. Okay, so this would give me the covariant field strength tensor. Of course, this is not a different object. It's still made up of the same electric and magnetic fields, just written differently. Okay, and if you'll recall, a covariant index transforms using the matrix lambda transpose inverse. And it's also useful to note that in 4 dimensions, there is a particular tensor, which this tensor is useful when we write down Maxwell's equations. So this tensor is called the Levi-Civita tensor. Okay, and this tensor is defined like so. It's a rank 4 tensor, and it's defined so that epsilon 0, 1, 2, 3 is +1. And if I now exchange any 2 indices, okay, I would pick up an extra minus sign. So for example, epsilon 0, 2, 1, 3 would be the same as epsilon 0, 1, 2, 3 up to a minus sign. So in this case, this would be -1. Okay, and if I make another exchange, so exchange 1 and 3, this would be related to epsilon 0, 2, 1, 3 by a minus sign, or it would be related by 2 exchanges to epsilon 0, 1, 2, 3. So this would just be +1. So in this way, I can figure out all the components of epsilon mu nu rho sigma. So this is called a fully antisymmetric rank 4 tensor. So this is the generalization of epsilon ijk in 3 dimensions. This now what we have is a rank 4 antisymmetric tensor. Now the important thing about this tensor is that if I calculate the components in one reference frame, so frame S, and I know how to transform this into a new reference frame S prime, because this is a rank 4 tensor, so I would have to use 4 lambda matrices to transform it into the Levi-Civita symbol in the frame S prime. And what I would find is in the frame S prime, the components of the tensor are unchanged. That is, epsilon prime 0, 1, 2, 3 would also be +1, and so on. Okay, all the other symbols, all the other components of this tensor would be exactly the same. So such a tensor where all the components stay the same no matter which frame you calculate it in is called an invariant tensor. That is, the components do not change from one reference frame to another. Now, using this Levi-Civita symbol, or this Levi-Civita tensor, we can define a dual field strength tensor which is also contravariant. So this is denoted as f twiddle mu nu, which is written as half epsilon mu nu rho sigma f rho sigma. Okay. And in matrix notation, we could work out what this is. And we would get, in matrix notation, something that looks like this. So you can see that this dual field strength tensor exchanges the locations of electric and magnetic fields inside the tensor. Okay, so our old f mu nu look like this, and now we exchange the location of minus ex by c, we replace that with minus bx, and everywhere we have bx, we replace that by ex by c. Okay, and if we do that, we would get this dual field strength tensor. Sorry, this should be Ez by C. Okay, so now that we've defined the field strength tensor and the dual field strength tensor, we can write down Maxwell's equations using these field strength tensors. One more thing that we'll need before we do that is to know how rho and J transform under Lorentz transformations. And you can show that rho by C and Jx, Jy, Jz, these transform like a 4 vector, which I can define as the current 4 vector. Okay, or the charge current 4 vector. So finally, putting all this together, you can show that Maxwell's equations can just be written in this form. So let me write those out here. Partial alpha f alpha beta is j beta, or 4 pi j beta, and partial alpha f twiddle alpha beta is 0. So you get very elegant expressions for Maxwell's equations, and if we count how many equations we have, so this equation has the free index beta. Okay, so beta can take values 0, 1, 2, 3. So this is actually 4 equations. And similarly, this equation has one free index beta, which is also 4 equations. So we get 8 equations. And I'll leave it to you to check that this results in Maxwell's equations, okay, by plugging in the field strength tensors and taking the components explicitly. However, one thing that you can see quite clearly is if beta is equal to 0, then the quantity here has charge density here. So this would give you Coulomb's law. The 0th component of this would give you Coulomb's law. Whereas beta is 1, 2, 3 would involve the current density, so those would give you Faraday's law. And similarly over here, beta is 0 would give you the no magnetic monopoles law. And beta is 1, 2, 3 would give you Lenz's law. Okay. And now, by the form in which this is written, we can see that this satisfies our criteria for a physical law, in that the left-hand side of this equation transforms like a 4-vector. There's only one free index beta. And the right-hand side of this equation also transforms like a 4-vector. There's only one free index beta. And similarly, in the second equation, there's only one free index beta for this 4-vector. And on the right-hand side, we're saying that this 4-vector is 0, so it transforms like a 4-vector. Okay, so automatically, just by writing it using the proper 4-vector notation and correctly identifying the components of tensors and vectors, we see that Maxwell's equations preserve the same form under special relativity transformations. Okay, so Maxwell's equations are compatible with the principle of special relativity. And let's write down one more thing, which is one thing that you're familiar with is the Lorentz force law. That is, if I have a charged particle with a mass m and electric charge E, what is the force felt by this particle in the presence of an external electromagnetic field? Okay, and so this would come under Newton's laws. So the force that such a particle would feel would be E times the electric field plus V cross B. Okay, so this is what we call the Lorentz force. And in Galilean relativity, we would say that this force produces an acceleration. So this would produce an acceleration of the particle, or a change in momentum, okay, through this equation. So the force would lead to a change in momentum. Now, we can ask, is this law consistent with special relativity? And again, we can write this using tensors and 4-vectors, and we can see, or you can check that you can write this law in the form dp mu d tau is equal to E u alpha f alpha mu. Okay, where u alpha is the velocity 4-vector and f alpha mu is the field strength tensor. Okay, so this would be the Lorentz force law. And you would see that, well, of course, this transforms like a 4-vector. Tau is invariant. Tau is the proper time in the rest frame of this particle. And the right-hand side also transforms like a 4-vector because we've contracted these indices. So there's only one free index mu, and which is a contravariant index. So this also transforms like a 4-vector. And E, we've assumed, is the rest frame charge is a Lorentz invariant quantity. Okay. However, this equation has 4 components rather than 3 components. You can check that for mu is 1, 2, 3, you would recover exactly the Lorentz force law, which we're familiar with in Galilean relativity, except this vector p would be 3 momentum of special relativity, not 3 momentum of the standard 3 momentum that we're familiar with from Newton's laws. Now you could ask, what does the mu is equal to 0 component tell you? And there's already a hint here. Since P0 is the energy of the particle, or E by C, the 0th component would tell you what is the rate of change of energy of the particle with time, or with proper time. And this would be related to the power delivered to the particle. Okay, so this would be equal to the power delivered. Okay, so that's how you interpret the mu is equal to 0 component.